Hi guys, today I want to go over the rest of the slideshow that we didn't get to today. I'm pretty sure, hopefully, that starting at slide 7 with just the discrete masses that you can, that you feel comfortable applying the equation that I have here. And of course, it works in the y and z direction too. So that's all nice and good if you have just separate, particles, all right? But when we talk about a solid body, right, it's a continuous distribution of particles, right? If I've got that, right, and I'm trying to figure out sort of what's the center of mass of that thing, I need to take little chunks of mass and add them up. Right, sorry, I'll say how far away it is from the origin. I need to take all these little tiny bits of mass all around this object and add them up, right? Well, if you're adding infinite things, you know that baby's going to go to an integral. So that x center of mass is 1 over the mass, and instead of the sum of mixi, it'll turn into an integral of x dm, right? I'm integrating over the mass. So I get all my little baby dm's. And that x is this value of x right here is where that value of dm is that you're trying to add up. This is lovely, but not very useful, right? Because what does it even mean to add up, to integrate over mass, right? So how do we actually do it? Okay, it's nice to have the theory, but sometimes you just want to know how to do it. And let's just start by talking about a uniform object. That'll be easier. And then we can expand to non-uniform. What does uniform even mean? Uniform means that it's a constant density. Okay? And so hopefully you remember that density is mass over volume, and we can switch that around and write m equals rho v. This is quite a useful form right here. So if I was interested in dm, right? So dm is going to be rho, because rho is constant, dv. So, and I say this rho is constant, but this is actually a general thing. It's just that rho is the value of density at that point where the dm is. So this is the key here. So, right, the total mass, right, that's the total mass. So all of these are exactly the same thing as each other, okay? But we're just trying to figure out what can actually be useful, right? Because I had the x center of mass was 1 over the total mass, right, x dm. Now I'm going to put in this useful form. Instead of dm, I'm going to write rho dv, okay? And for this uniform object, rho is constant, so I'm going to write rho over m, integral of x dv. Now, can you figure out what rho over m is? If you look up here, rho over m is going to be 1 over v. So this is how we get this. Now this is going to be more useful, okay? This is for 3 dimensions, and you integrate over volume, which I'm not sure if you've done before. So it's more useful, but it's not super useful. If I just let you at this, you probably wouldn't know what to do. Maybe I'm wrong. But let's actually get a little bit more useful. To make something more useful, I need to introduce to you 3 kinds of density. One is the one that you're used to, is volume density, and that's rho is m over v, okay? There are also things called area density and linear density. What we're doing right now is very useful. It's a useful strategy that we're going to use a couple different times this year, and so you're going to see this a lot. So, if rho is m over v, so that's volume density. Area density is going to be m over a, and linear density is going to be m over l. These common variables are sigma for area density and lambda for linear density. Okay, so those are useful. Something that we can do here is we can say, okay, that linear density at any point is that little tiny mass divided by that little tiny volume. Okay, and so we can do that for all of these. And lambda is dm over dx. So finally we can get dm, right? dm sigma dA, and this is what you're going to actually use, because you're like, oh my gosh, I can integrate over one dimension at a time, right? Okay, so that's a lovely thing. So now we can write this center of mass position. It's 1 over the total mass, integral of x dm, and now we can write our dm using what we did in the last slide, and we can say lambda x dx, okay? And that was because lambda dx was dm, right? Okay, I actually don't want those little things there, because this thing is so useful, it gets a box, okay? And this is actually good for uniform and non-uniform, okay? Because the only difference is if it's uniform, then lambda's constant and it just gets pulled out. If it's not uniform, then lambda is just a function of x and it just gets integrated in the thing. Okay, so let's do an example. So let's do a uniform bar of mass. M is 12 kilograms and length 3 meters. Okay, so the first thing we want to do is calculate the linear density. That's mass over length. So that's 12 kilograms divided by 3 meters. So linear density is kilograms per meter. Talk about units for a second. When I, like if you just think about normal density, it's mass per unit volume, so it's kilogram per cubic meter. And so linear density being kilogram per meter hopefully makes you happy. All right, so let's actually calculate the center of mass. So it's 1 over the total mass, and we're going to go from 0 to L of lambda x dx, right? X is going from 0 to L. Here's our bar, and here's my origin, and that's my length, okay? And so I'm going to go, right, this is x. And so I'm going to integrate from 0 to L over x. All right. And when I said over x, I meant like that's the, like the dx. Okay. So let's plug in things. So the total mass was 12 kilograms. And the lambda was 4 kilograms per meter. And we get an x dx, right? Well, because lambda is constant here, 4, I can just pull it right out. And I get 1 over, and what units is that? Meters. And I'm keeping the units in so that you don't lose sight of what we're actually doing here. Because when we integrate that x dx, well, let's see what happens. Let's see. Okay. We're going to integrate x dx, and what are our limits? We're going to go from 0 to 3, right? All right, let's do it. So 1 over 3, now I'm just going to take away the units because I'm playing around with stuff. So the integral of x dx is x squared over 2. And we're integrating from 0 to 3. So I'm going to take out that 2. Okay, sorry, the half, my bad. And it's going to be 3 squared minus 0 squared. So we get 3/2 of a meter. Oh my goodness. Where's that? Well, if that's 3, well, by golly, for a uniform body, the center of mass is at the geometric center. Okay? So that's really useful. Okay? That's for a uniform body. Let's make it interesting, shall we? What about a non-uniform bar? Okay, same mass. Oh my goodness, that's a 3. Just kidding. Doop, boop, 3 meters. Okay, and here is the function of the linear density. It's 1 plus 4x. Okay, so now we have from 0 to L of lambda x dx. We can't just take out lambda because it is a function of x. And so if we start plugging in things, we have 1 over 12 kilograms, that's the total mass, 0 to 3 meters, and lambda is 1 plus 4x, and now we have x dx. So if you would like to go and solve that, I will pause, and then we'll come back and we'll finish it together. So we have x plus 4, oh my goodness, 1 over 12 x plus 4x squared dx, 0 to 3. So we have 1/12. We have x squared over 2 plus 4x cubed over 3. And evaluated it from 0 to 3. So we get 1/12, 1/2, 3 squared plus 1/3, 3 cubed, minus all that stuff at 0, which is just 0. And you get 1.1 meters, which is not the 1.5 meters we got before, right? Because it has this nonlinear density. Okay, so hopefully that helped explain some of that. And remember, even if you don't have a lot of problems right now with this, we're going to be using this strategy in a couple different places this year. Okay, thanks.